The greatest source of confusion for many students studying tensors is Einstein notation. It quickly becomes a huge headache trying to keep track of all these superscripts and subscripts, not to mention trying to remember exactly how to raise and lower indices, or attempting to figure out what crazy equations like this could possibly mean. Here's the thing though, you actually can understand Einstein notation. In fact, not only understand it, but learn how to use it efficiently in almost any circumstance. And in these next series of videos in this playlist, I will teach you how. We will begin by first learning how to use this notation to express vectors and dual vectors acting on each other. We will then work up to expressing common vector operations, as well as performing matrix multiplication. Our final goal will be to understand everything in this beast of an equation and know how to manipulate any type of tensor. In this video, we will focus on step 1. This will lay the foundation so that in a few more videos, you will actually understand everything on the screen. Okay, so let's get started. In order to be able to use Einstein notation efficiently for vectors and dual vectors, there are 3 rules that you must memorize. The first rule is every time indices are repeated, they are implicitly summed over. The second rule states that we will use upper indices for the components of vectors and lower indices for basis vectors. And the final rule is the mirror image of the second. Dual vectors will have components that are lower indices, but bases that are upper indices. Now, there are actually a couple more rules, but we won't need them to understand vectors and dual vectors. So I'll explain those in a future video. Okay, so how do we use all these rules? We'll begin by using them to express a vector. Remember, a vector is an element that lives in a vector space. And if the vector space is the familiar 3D space we usually work in, or as mathematicians would call it, R3, then a vector will have 3 components, one in each of the x, y, and z directions. So if we apply this second rule, that vectors will have components with upper indices, we can rewrite any vector with each of its components as follows. Where v1, v2, and v3 are just real numbers, and x hat, y hat, and z hat are the standard basis vectors in the x, y, and z directions. Now, in order to write the bases with lower indices, we will need to introduce a new notation. We will label x hat as e1, y hat as e2, and z hat as e3. And I'd like to stress here that we have not done anything to the actual bases. We've simply introduced a new way to refer to them. The benefit to this new notation is that it allows us to write the vectors as a sum. And if we choose the letter I as an index, it will be the sum of vi, ei, where I goes from I equals 1 to 3, where again, the upper index is the component of the vector and the lower index is the basis. Now, we just arbitrarily chose the letter I here as the summation index, but we could just as easily have chosen another letter, say mu, and it would mean the exact same thing. So since the letter chosen as the index here is arbitrary, it gets the name of a dummy index. And in general, when using Einstein notation, any index that is summed over will be called a dummy index. If we now apply the first rule, we don't even need to include this summation symbol. Anytime we see an index that is repeated, it will just mean that it is summed over. And in this case, it is summed over 3 dimensions. But in other cases, like in special relativity, it will be summed over 4 dimensions, with time being one of them. In general, though, it will be clear based on the context how many dimensions you are summing over. Okay, so that's how a vector can be expressed. What about a dual vector? In order to express a dual vector, the first thing we'll need to do is to define a basis. And the way that the basis is defined is as follows. We'll use the third rule, and we will require that a basis dual vector acts on a basis vector in a way that satisfies this equation, where delta mu nu on the right is the Kronecker delta symbol. This is a tensor that I will explain more about in a future video, but for now it will suffice to know that it equals 1 whenever nu equals mu, and it equals 0 whenever nu and mu are not equal to each other. So any basis vector in the dual space satisfies this equation and is fully defined by it. It is then straightforward to express a dual vector in terms of these bases. We simply will write the components with a lower index and utilize the rule that repeated indices indicate an implicit sum. And again, this index is a dummy index that is summed over 3 dimensions, but it could be a different number in other contexts. Okay, so now we are ready to see how dual vectors act on vectors in this notation. If we simply use the results we have just derived, we can write phi acting on a vector v as this expression, where there are 2 sums implied, one over nu and the other over mu. Now, one of the strengths of Einstein notation is that since these indices are the things telling us how to sum, we can change the order of this expression around and it will still mean the same thing. So, for instance, we can swap the two middle terms and get this. And these last two terms are just equal to the Kronecker delta, so we can rewrite this expression as follows. And since the Kronecker delta equals 1 only if nu equals mu, but is 0 otherwise, then we can simply change mu to nu. And we finally get to our desired result, a way to express a dual vector acting on a vector. And this makes perfect sense. The expression on the right is a sum of the product of components of the dual vector and vector, so it must be a real number. And remember, phi is just a linear functional, which is a map from a vector space to the real numbers. So we indeed get that phi maps the vector v to a real number. Okay, now we'll end with expressing how a vector acts on a dual vector. This one is actually simple. It's simply defined as being the same thing as the dual vector acting on the vector. And therefore, v acting on phi is equal to this. Okay, so I'll wrap it up there. I hope you found this video helpful and all of these expressions make complete sense to you now.